Welcome back to Physics Galaxy, and today we're going to solve some electrodynamics questions which were asked in last CSIR NET examination. And this question states, two identical cubes are shown in figures A and B. The magnitude of the magnetic field at the center of the cube in A produced by the currents as shown is B naught. Okay, the magnitude of the magnetic field at the center of the cube in B will be. Okay, so first of all, we have given a loop. So we have a loop, this configuration. We have a loop formed by four currents. So this is the current going like this. Okay. And at the center magnetic field is B naught. So at the center magnetic field is B naught. That we know. So what we had to find is the magnitude of the magnetic field at the center of the cube in B. So in this configuration, we had to find the magnetic field at the center. Okay. Okay. All right. Now we know for this loop, magnetic field will be in this direction and its magnitude will be B naught. So somehow I had to form some loops. Okay. So how we can form some loops? So we can make loops like this. We had to add some currents, additional currents we had to add it. So if I can make first of the top loop, so I had to make it closed. So this way, if I can make this loop, then I had to introduce one more current here, one more current here. Okay. Similarly, this loop, the sideways loop. So this is the sideways loop. Then I had to introduce new current. So new current will be like this, and one more current will be like this. Okay, and in the back side, I had to form one more loop that will be like this. So here, here, this is the original current. Then again this current, so that will go like this, and then this way. So it should be going downward. So you can see all the currents in wherever there was no current initially, they cancel out. Okay, so all three currents cancel out, but the resultant, what we have in the resultant is we have four loops, sorry, three loops. So first loop is the side loop. Suppose this loop, side loop, and current is going like this, right? And then we have one more loop that is at top. So at top we have one more loop, so that is going like this, right? So this is the top loop, and then we have the back loop. So that is, suppose let me draw it here, that is like this. Okay, so we have three loops. Okay, and the currents at this point, this edge, they will cancel automatically. So we again have the original configuration. So we had to find the resultant of these three loops at the center. So this is first loop, second loop, and third loop. Now all three loops, suppose this loop at the center will produce magnetic field in this direction, okay, perpendicular to with a magnitude B naught, and similarly the top one will produce the magnetic field in the bottom direction with the magnitude same B naught, and the third backward loop, this one, it will also produce magnetic field in the forward direction B naught, and all will have the same magnitude B naught, B naught, B naught, right? So because they are now perpendicularly oriented, so the net magnitude will be root 3 B naught, which is option number 1. The next problem is the charge density of the electron cloud of a hydrogen atom is given by rho of r. So this is our rho of r, which is just electron cloud density, where A is some characteristic length. The potential energy due to the interaction between the proton, which is sitting at the origin, and the electron cloud is given by. And these are our four options. So what we have is a proton. So this is our proton at the center of charge E, and this is our electron cloud, suppose, okay, which is surrounding our proton. Okay, now what we have to do, so what we can do, we can decompose that electron cloud in shells. Okay, we can decompose that electron cloud with this infinitesimal shells of finite radius r. Okay, and then we'll integrate from 0 to infinity. So we can integrate 0 to infinity and calculate the potential energy of the system. Okay, so we know already. So we know if we have a shell, suppose we have a shell of radius r, and at the center suppose we have a charge plus e, and its charge is suppose dq, then potential energy will be u equals to e dq divided by 4 pi epsilon naught r. So this is the potential energy of the system, because okay, so this is the charge times the potential of a shell, right? Okay, now what we need to do is to integrate, but before that we need to find what is dq. So dq is nothing but the charge density times the volume, and volume is taken that of a shells, because this is the shell and we have to take the volume of this shell. So this is the volume of the shell, and volume will be equals to 4 pi r squared dr. Okay, and now we'll just substitute and we'll get final answer. So u equals to e divided by 4 pi epsilon naught r, where to integrate from 0 to infinity, and then rho times 4 pi r square dr, right? And rho, we know rho equals to uh, rho is given minus e by 8 pi minus e by 8 pi a cube e to the power minus r by a. So I just substitute and we'll get the final answer. So 4 cancels out, r cancels out. So I have e, then epsilon naught, the minus sign, and then we'll have integral 0 to infinity e by 8 pi a cube e to the power minus r by a, and then we have r dr, right? And so we'll have minus e square by 8 pi epsilon naught a cube, and then integral r e to the power minus r by a dr 0 to infinity. And if you check this integral, it will come out as minus a square. So this will be minus a squared. The final answer will be, so final answer will be u will be equals to minus e square by 8. Okay, pi we already cancelled out. Okay, so there is no pi here. Oh, there is no pi. Minus e square 8 epsilon naught, and here will be only a. So this will be our final answer. Minus e square 8 epsilon naught a. Okay, but there is one more pi. Okay, so there was one more pi here. Right, so there was one more pi. So this is your final answer. The next question is a circular loop of radius a, which is in the xy plane. Okay, so this is our circular loop in the xy plane, and a square loop outside b. This is our square loop outside b in the xz plane are kept at a distance r. Both carry current I as shown in the figure. If r is very large, then the dimensions a and b, the torque exerted by the square loop by the circular loop is. So we have to find the torque. So this is what we have to find, torque. Now, what we can say is that because these are current carrying loops, so this one we can consider as one dipole, suppose C, circular dipole, and this we can consider another dipole, square dipole, okay, S, and the current will give us basically the direction. Okay, now what is torque? We know torque we can find torque is equals to mu cross B. So torque exerted on the circular loop by the square loop, टॉर्क एक्सर्टेड ऑन स्क्वायर लूप बाय द सर्कुलर लूप. ओके, इसकी वजह से कितना टॉर्क इस बढ़ रहा है. Okay, so mu will be of S and B is the magnetic field due to circular. Okay, mu cross B. Now what is mu? Mu of this square. mu of square, we can simply write mu of square will be equals to current times the dimension, this area, so that will be b square, right? And then what do we have to find? The magnetic field. Magnetic field due to magnetic field, so b c. So this is the magnetic field due to this one circular uh, current loop. So because you can see that it's a dipole like this, so magnetic field lines will be let me draw it like this. So magnetic field lines will be like this. This will be the magnetic field lines, right? And at this line, which is this line, so for this line, the magnetic field will be pointing downwards, right? So magnetic field will be pointing downwards, and its magnitude will be given by. So there will be no radial component. So magnetic field will be given by mu naught by 4 pi m sine theta divided by r cube, right? Where m is magnetic moment of this circular loop. So that is equals to I times pi a square. So that's it. Now we have to substitute m here, and then we have to substitute mu s here and b here. So that's substitute and final answer. So the torque will be equals to mu s. So mu s, so I b square, and if we can see, so mu and b are perpendicular, so sine 90 equals to 1. So then we have b equals to mu naught by 4 pi. So m again is I pi a square, then sine theta. So again theta equals to 90, so sine 91 and r cube. So it equals to mu naught by 4 pi I square b square a square by r cube, and it will be pointing. Now we have to find also the direction. So mu cross b. So mu is uh, like this. Okay, so this is mu. Like, so here we have mu, and b is pointing downwards. So mu cross b will be in the x direction. Mu cross b, but in the minus x direction. So we'll have minus x cap. One more question is, a thin circular wire loop of mass m having radius r carries a static charge q. The plane of the loop is held perpendicular to a uniform magnetic field B along the z-axis passing through its center, as shown in the figure. The loop, initially at rest, can freely rotate about the z-axis. When the magnetic field is switched off, the loop starts rotating with an angular frequency. Okay, so I have to find the angular frequency, omega. So actually, what we have here, so we have a circular loop. So this is our circular loop of radius r, and charge it carries is q. And it says that it's free to rotate about this z-axis omega. Okay, so what happens is that the loop initially at rest can freely rotate. Okay, the magnetic field is in this direction, z direction. So let's put the magnetic field. So this is the magnetic field direction, b. Okay, in the z direction. So it's suddenly turned off and it starts to rotate. So why it starts to rotate? Because there is a change in flux. So we know AMF equals to minus d phi by dt, or we can say del phi by del t, right? And EMF we know equals to integral E dot dl. So initially what we have here, so initial flux was equals to B times the area, so that is equals to pi r square. So this is the initial flux. Finally its magnetic field is turned off, so the flux will be zero. So change will be equals to minus b pi r square. So this will be the change in flux. Okay, and this change in flux will create the electric field. So we can say integral, or the EMF, electromotive force, will be equals to b pi r square by delta t, right? But we have to find the frequency. So for that we had to calculate first electric field. So we can write E, and dl will be 2 pi r equals to B by R square by delta T. So what we cancel out here is, we can cancel out uh, pi and r from here. So we have electric field is given as equals to B r by 2 delta t, and this will be in the phi cap direction. Okay, so what basically we have here is that when we stop the magnetic field, there will be electric field, and which will be in the phi cap direction. Okay, and this electric field will try to rotate the circular loop about this z axis. Okay, so the force will be equals to q times e. So that will be the total force on this loop. So we can write F which equals to Q times E. So B R 2 delta T. So now we can calculate the torque. Torque will be equals to R cross F. So R and F will be perpendicular at each point. So we can have simply B R square by 2 delta T. Now torque is rate of change of the angular momentum. So delta L by delta T. And from here we can calculate the omega, because initially L initial was equals to 0, there was no angular momentum, but L finally will be equals to I omega. So the change will be simply I omega. So that is here. So we'll have simply B R square by 2 delta T equals to I omega by delta T. So delta T cancels out, and we know for simple loop it will have I equals to mr square. So we have B R square by 2 which equals to, okay, here it was Q also, Q. So Q was here, and then I will be mr square times omega. So r square cancels out. So we have finally omega with which this loop will rotate. That will be equals to Q B by 2m.